Hello, everyone. So looking at the title of this section, we can see that it is on friction. Similarly, by looking down at the image here at the bottom, we see a man pushing a couch. The image seems to show the man struggling at first to push the couch and then start to move out in this image here. This seems to represent a resistant force opposite to the pushing force the man is applying. And this resistance force is going to somehow involve friction. So push your hand across your desktop and feel the force called friction, opposing the motion. Push your book across the desk. When you stop pushing, the book will continue moving for a little while. Then it will slow down and stop. The frictional force acting on the book gave it an acceleration in a direction opposite to the one in which it was moving. Looks like I was correct that friction is opposite to the push we give to an object, since the push would have been in the same direction that the book is moving. So far, you have neglected friction in solving problems, but friction is all around you. You need it to both stop or start a bicycle and a car. If you have ever walked on ice, you understand the importance of friction. Now, ice is very slippery, right? So does that mean that it doesn't have a lot of friction? I think that the article will likely talk about how different surfaces might affect this frictional force then. Now, reading this next section heading here, static and kinetic friction, I think this means that there are going to be two types of frictional forces that we will be going over. There are two types of friction, both always oppose motion. When you push your book across the desk, it experiences a type of friction that acts on moving objects. This force is known as kinetic friction. So I was right about there being two types. And it is exerted on one surface by another when the two surfaces rub against each other, because one or both of them are moving. This makes sense because that kinetic friction is with an object that experiences motion, because the word kinetic means related to or resulting from motion. It makes sense that it makes me think of something like a kinesthetic workout where you move around a lot. To understand the other kind of friction, imagine trying to push a heavy couch across the floor. You give it a push, but it does not move. Because it does not move, Newton's laws tells you that there must be a second horizontal force acting on the couch, one that opposes your force and is equal in size. It's equal in size because if it was greater than the force that's pushing against the couch would instead be moving toward us instead of staying in place. This force is static friction, which is the force exerted on one surface by another when there is no motion between two surfaces. Now, static means lacking in movement. When I hear the word static, I think of other words like maybe stasis or just stopped in place. You might push harder and harder as shown in figures 5-A and 5-B, which is here and here. Man lightly pushing the couch, it looks like, and then more forcefully pushing the couch, but the couch still hasn't moved. But if the couch still does not move, the force of friction must be getting larger. Thinking back about what I read about kinetic friction and looking at the image of the man moving the couch, I can now see that in part A, the man has yet to push against the couch, and B, he is pushing against it, but it has not overcome the static frictional force, and therefore the couch still isn't moving despite him pushing. And in part C, he has to overcome the static force and is now probably feeling the kinetic frictional force since it's now in motion. Finally, when you push hard enough, as shown in figure 5-8C, the couch will begin to move. Evidently, there is a limit to how large the static frictional force can be. Once your force is greater than the maximum static friction, the couch begins moving, and kinetic friction begins to act on it instead of static friction. So it looks like I was correct in guessing that the force of friction between them switches once the couch began to move. A model for friction forces. Now, a model is typically an example, so we will probably get another example of frictional forces in play in this section. What does frictional force depend on? Well, what does frictional force depend on? Earlier, with the example of walking on ice, I was thinking that the surface that the object was on plays a role. Maybe the size of the area of contact or the amount of weight that the object has also plays a role. The materials that the surfaces are made on plays a role. For example, there is more friction between skis and concrete than there is between skis and snow. It may seem reasonable to think that the force of friction also might depend on whether the surface area in contact or the speed of the motion, but experiments have shown that this is not true. Okay, I didn't think about the speed of the object, but it is interesting that the surface area does not play a role. So that means that no matter how large an object is, it would experience the same amount of friction, regardless if it was massively, covering a huge amount of surface or just like a pinprick on the surface, it would suffer the same amount of friction. That's interesting. The normal force between two objects does matter, however. Now, the normal force, as you might have heard in some other in previous lessons dealing with forces, is another way of just saying the weight of an object, of a force due to gravity pushing down. So the amount of weight the object is have, and the more it pushes against the surface, the greater than the frictional force, even though it does not depend on how much surface area that force is applied to. The harder one object is pushed against the other, the greater the force of friction that results. So, all right. So in conclusion, from this text, we learned that friction is a force opposite the motion. So if the couch is moving in this direction, the frictional force is in this direction, opposite the motion and opposite of the per man pushing it. And that it depends on whether the object is in motion or the object staying still. If it's in motion, it's suffering from kinetic friction and a kinetic frictional force. If it's staying still, then the man pushing it will feel the static friction and the static frictional force. And the surfaces on, as well as how heavy or that normal force that the object has, also plays a role. So pushing a couch on, say, carpet will be a lot harder compared to like a hard wood floor, probably. And a heavy couch compared to maybe a light couch would be much harder to push as well. So I think this wraps up this section on friction. Thank you very much and have a nice day.